Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will discuss the first order higher degree ordinary differential equation part 3. In the first part, we discussed first order higher ordinary differential equation when it is solvable for P. P means dy by dx. In the second part, we discussed the first order higher degree ordinary differential equation when it is solvable for y. And in this part, we will discuss first order higher degree ordinary differential equation when it is solvable for x. First of all, we recall last topics. First order higher degree ordinary differential equation. A general form of the first order higher degree ordinary differential equation is dy by dx raised to n plus f1 dy by dx raised to n minus 1 plus f2 dy by dx raised to n minus 2 plus fn minus 1 dy by dx plus fny equal to 0, where f1, f2, f3 up to fn are functions of x and y. To solve this type of differential equation, we will take the dy by dx equal to p. Then we have a p raised to n plus f1 p raised to n minus 1 plus f2 p raised to n minus 2 up to fn minus 1 p plus fny equal to 0. Call it equation number 2. There are three methods to solve this type of differential equation. In the first part, we studied solvable for P method for first order higher degree ordinary differential equation. In the second part, we discussed solvable for Y method for first order higher degree ordinary differential equation. And in this lecture, we will discuss the first order higher degree differential equation when it is solvable for x. Let us see first order higher degree ordinary differential equation when it is solvable for x. So this is our first order n degree ordinary differential equation. P raised to n plus f1 p raised to n minus 1 plus f2 p raised to n minus 2 up to fn minus 1 p plus fny equal to 0. Call it equation number 1, where dy by dx equal to p. Now, if this differential equation 1 can be expressed in the form of x equal to some function of y and p, then it is solvable for y. In this case, first of all, we differentiate x equal to yp form with respect to y. Then we get dy by dx by dy equal to del f by del y plus del f by del p into dp by dx, and it is a form of function yp and dp by dy. Now this differential equation can be rewrite as 1 upon p del f by del y plus del f by del p into dp by dy, because we have a dy by dx equal to p, so dx by dy becomes 1 upon p. Now this is our first order differential equation in variable y and p, and dp by dy is our first order derivative present in this differential equation. After solving this differential equation, we get the general solution of the form g of ypc equal to 0. Call it equation number 4, where c is arbitrary constant. Now eliminate p from equation number 3 and 4, and then we get the general solution of our original differential equation p raised to n plus f1 p raised to n minus 1 plus f2 p raised to n minus 2 up to fn minus 1 p plus fny equal to 0. That is the method to solving our first order higher degree ordinary differential equation when it is solvable for x. Here, first of all, we should convert our differential equation in the function of x equal to f of py. Then and then this method is applicable. Let us see some example related to this topic. Dy by dx whole square minus x dy by dx plus y equal to 0. This is our first order second degree ordinary differential equation. If we take dy by dx equal to p, then our differential equation becomes p square minus xp plus y equal to 0. Now, if first of all p square minus xp plus y equal to 0 can be rewrite as xp equal to p square plus y, and here x can be written as x equal to p square plus y upon p. That can be also written as x equal to p plus y by p. Call it equation number 1. Now equation number 1 is a form of x equal to f of yp. Therefore our differential equation 1 or our original differential equation can be solvable for x. Now we differentiate equation x equal to p plus y by p both sides with respect to y. Then we get dx by dy equal to dp by dy plus 1 upon p minus y upon p square dp by dy. Here we differentiate both sides with respect to y, and as we know that dy by dx is p, that implies dx by dy equal to 1 upon p. So we will put in our previous step, then we get 1 upon p equal to dp by dy plus 1 upon p minus y upon p square dp by dy. Here 1 upon p cancelled from the both sides, then we get 1 minus y upon p square dp by dy equal to 0. So we obtained 1 minus y by p square into dp by dy equal to 0. Here we have a two factor 1 minus y by p square and dp by dy, but first factor 1 minus y by p square is not a first order first degree ordinary differential equation. Here we will consider only first order first degree ordinary differential equation, which is dp by dy equal to 0. So we can say that p equal to c, where c is arbitrary constant. Now we put p equal to c in our original differential equation, p square minus xp plus y equal to 0. Then finally we get the general solution c square minus xc plus y equal to 0, or y equal to xc minus c square be a general solution of our original differential equation dy by dx whole square minus x into dy by dx plus y equal to 0, or p square minus xp plus y equal to 0. So here this is the method when our differential equation is solvable for y. When this method is applicable for the first order higher degree ordinary differential equation, if first of all we can express our differential equation in the form x equal to some function of y and p, then we differentiate with respect to y, and from that we find the only first order first degree ordinary differential equation. First of all, find the general solution of first order first degree differential equation in the terms of y and c, and put in place of p in our original differential equation this solution. Then we get the general solution of first order higher degree ordinary differential equation in when it is solvable for x. Here this is the last topic of first order first degree and first order higher degree ordinary differential equation. Here we completed this topic. Here we completed first order differential equation, and first of all recall our topics. Here differential equation, and this is divided into three parts in our syllabus. First of all, first order first degree ordinary differential equation, in which we studied formulation of differential equation, separable variable method for homogeneous and simple form, and exact non-exact differential equation, as well as first order linear differential equation and Bernoulli's differential equation. In the second part we studied first order higher degree ordinary differential equation, and methods of this are solvable for p means dy by dx, solvable for y, and solvable for x. Now our next topic is higher order linear ordinary differential equation, and we will discuss in next chapter. Thank you very much.